Hi, Stu Schwartz, MasterMathMentor.com. This is video AB29a. The topic is Riemann Sums, and it covers the AB manual pages 175 through 177. This is an example of sigma notation, and you should have learned it in Algebra 2 or Pre-Calculus. This video assumes you understand its use. If you didn't learn it, or perhaps are still rusty on it, I suggest you do a quick review. It is covered on page 277 of your AB manual, and there is an AB video that explains it in the review section. It is called Video R5. On the screen is the graph of the function f of x. Pause the video and attempt to approximate the integral from 0 to 4 of f of x dx, the area under the curve. We now draw the same graph, but we will approximate our area using areas of rectangles. The first graph has 2 rectangles, the second 4 rectangles, and the third 8 rectangles. Stop the video and approximate the area of each of these rectangles to approximate the area under the curve. Let's now get specific. Let's suppose that our graph is f of x equals x squared plus 1. Now we can find the approximation of the integral from 0 to 4 of f of x dx using 2 rectangles, 4 rectangles, and 8 rectangles. With 2 rectangles, each of them having the same base, the area is equal to A1 plus A2, which is BH1 plus BH2, where B is the base of each rectangle. We can now factor out the B and write the area as B times the quantity H1 plus H2. And this will equal B times f of 2 plus f of 4. Since f of x equals x squared plus 1, f of 2 is 5 and f of 4 is 17. So the area is 2 times 5 plus 17, or 44. It should be clear that this grossly overestimates the true area under the curve. Let's now do the same, but with 4 rectangles. A equals A1 plus A2 plus A3 plus A4, which is BH1 plus BH2 plus BH3 plus BH4. We can factor out the B and get B quantity H1 plus H2 plus H3 plus H4. H1 is the height of the first rectangle, which is f of 1. H2 is f of 2, H3 is f of 3, and H4 is f of 4. So we have B quantity f of 1 plus f of 2 plus f of 3 plus f of 4. The base of each rectangle is 1. So we have 1 quantity 2 plus 5 plus 10 plus 17, and we get 34. It should be clear that this is a better approximation than we had in the first picture with 2 rectangles. It is still an overestimation, but not as bad. Let us now move to 8 rectangles. A will be equal to A1 plus A2 plus dot 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 plus A8, which is BH1 plus BH2 plus dot 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 plus BH8. We can factor out the B and get B quantity H1 plus H2 plus dot 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 plus H8. H1, the height of the first rectangle, is f of 0.5. H2 is f of 1. H3 is f of 1.5. H4 is f of 2. H5 is f of 2.5. F of H6 is f of 3. H7 is f of 3.5, and H8 is f of 4. So plugging those into the formula, we get A is equal to the base, which is 1/2 times the quantity 1.25 plus 2 plus 3.25 plus 5 plus 7.25 plus 10 plus 13.25 plus 17, and we get 29.5. This is much more work, but we get a much better approximation than we did when we did 4 rectangles, and certainly when we did 2 rectangles. Going through this tedious process, several things should be apparent. First of all, it's not really necessary to draw the function and the rectangles. Secondly, the more rectangles you create, the more work you need to do. That's a lot of arithmetic, but the better the accuracy. You can see in the picture above where we created 16 rectangles, then 50, then 100. And notice that the greater the number of rectangles, it looks like we're actually calculating the area under the curve. However, we are really calculating the area of 100 rectangles. The more rectangles you create, the smaller the error in calculating the error for each rectangle. So as the number of rectangles approaches infinity, the error for each rectangle approaches 0. And if you have an infinite number of errors, each approaching 0, the total error should approach 0. And if you have no error, you have the true area under the curve. The formula I'm about to present uses sigma notation, which should have been covered in your pre-calculus course. Sigma means summation. If you are a bit rusty on sigma notation, you may want to go to the review section in the AB manual on page 277, and you will get a refresher on sigma. So, the integral from a to b of f of x dx, representing the area under the f curve, will equal the limit, as n approaches infinity, of the summation, where I runs from 1 to n, of a sub I, meaning a sub 1 plus a sub 2 plus a sub 3, and going out forever. That represents the limit as n approaches infinity of the summation I equals 1 to n of b h sub I, because h sub I are the heights of each rectangle. And that will equal the limit as n approaches infinity of b summation I equals 1 to n of h sub I. We will see this in the upcoming examples. As an example, suppose f of x is equal to 4x plus 12 minus x squared. Our goal then is to find the integral from 1 to 5 of f of x dx, which is the integral from 1 to 5 of 4x plus 12 minus x squared dx, as shown in the figure. We will learn 4 approximation techniques, the first 3 of which are called Riemann Sums, named after the German mathematician Bernhard Riemann from 1826 through 1866. Riemann sums will find the sum of the area of rectangles. We will create 4 rectangles of equal base in our examples. Since we are interested in the area from 1 to 5, and there are 4 rectangles, the base of each rectangle is luckily 1. Such a simple value for the base won't always occur, so in general let's call the base b. We will define x0, x1, x2, x3, and x4 as the locations on the x-axis where we will build our rectangle heights. In this case, x0 equals 1, x1 equals 2, x2 equals 3, x3 equals 4, and x4 is equal to 5. And again, for this specific example, f of x is equal to 4x plus 12 minus x squared. We will start with left Riemann sums. A left Riemann sum uses rectangles whose top left vertices are on the curve. Our area, in this case, will be BH0 plus BH1 plus BH2 plus BH3, where the h's are the heights of the rectangle and b is the base. We can factor out the b and write that as b quantity h0 plus h1 plus h2 plus h3. Since the height at any location I is equal to f of x sub I, this becomes the area is approximately equal to b times the quantity f of x0 plus f of x1 plus f of x2 plus f of x3. So in our specific case, where f of x equals 4x plus 12 minus x squared on the interval 1 through 5, a is equal to b of f of 1 plus f of 2 plus f of 3 plus f of 4. So our left Riemann sum will simply be the base times the summation where I runs from 0 to 3 of f of x sub I. And in that case, we would have 1 times quantity 15 plus 16 plus 15 plus 12, which is 58. So for n rectangles in general, area will approximately equal to b times the summation where I runs from 0 to n minus 1 of f of x sub I. We will now approximate the integral from 1 to 5 of 4x plus 12 minus x squared dx, but we'll use right Riemann sums. Right Riemann sums use rectangles whose top right vertices are on the curve. We still have our values x0, x1, x2, x3, and x4 along the base of our rectangles. Our area for right Riemann sums will be BH1 plus BH2 plus BH3 plus BH4. And we can factor out the b and write that as b quantity h1 plus h2 plus h3 plus h4. The height of any rectangle I is equal to f of x of rectangle I, and therefore this becomes b times f of x1 plus f of x2 plus f of x3 plus f of x4. So when we do this for the specific case, we will say that the area will approximately equal to b times the quantity f of 2 plus f of 3 plus f of 4 plus f of 5. So our right Riemann sum area formula is a is approximately equal to b times the summation I equals 1 to 4 of f of x sub I. And when we use the specific example, we get a is equal to 1 times quantity 16 plus 15 plus 12 plus 7, and that gives 50. So for n rectangles in general, right Riemann sum formula is a is equal to b summation I equals 1 to n of f of x sub I. As shown in the graph, left Riemann sum, sometimes abbreviated LRS, builds rectangles starting with the leftmost x value. Right Riemann sums, RRS, builds rectangles ending with the rightmost x value. This one red left Riemann sum rectangle was generated as we build them from the left. The exact same blue right Riemann sum rectangle will be generated as we build them from the right. For all rectangles except the leftmost and rightmost, this will always occur. Both calculations, LRS and RRS, use exactly the same rectangles except for the leftmost and rightmost. If a function is increasing on an interval a left Riemann sum will under-approximate the integral, while the right Riemann sum will over-approximate the integral. For a function that is decreasing on an interval, a left Riemann sum will over-approximate the integral, while a right Riemann sum will under-approximate the integral. Concavity makes no difference. So let's determine the area under the curve f of x equals 3x plus 2 on the interval 3 to 5 with 4 rectangles. Our base will be the difference between the left and right x value, which is 5 minus 3, divided by the 4 rectangles, and the base is 1/2. So for left Riemann sums, the area will approximately equal to 1/2 f of 3 plus f of 3.5 plus f of 4 plus f of 4.5. And that becomes 1/2 times 11 plus 12.5 plus 14 plus 15.5, which is 26.5. For the right Riemann sum, the area will approximately be 1/2. And now we multiply that by f of 3.5 plus f of 4 plus f of 4.5 plus f of 5. That gives 1/2 quantity 12.5 plus 14 plus 15.5 plus 17. Notice again it uses the same values as the left except for the first and the last, and that area is 29.5. Although not necessary, we showed the graph of the left Riemann sum in red and the right Riemann sum in blue. The amount that the left Riemann sum under-approximates the true area is the same as the amount that the right Riemann sum over-approximates the area, and therefore the true area will be halfway between the left Riemann sum and the right Riemann sum, which is 28. We see this to be true as the shape of the area will be a trapezoid whose area is 1/2 the base, which is 1/2 of 2, times height 1 plus height 2, which is 11 plus 17, and our answer is 28. In number 2, we have f of x equals 9 minus 4x squared, and we want the area under the curve between x equals 0 and x is equal to 1, again using 4 rectangles. Our base will be 1 minus 0 divided by 4, which is 1/4. So the left Riemann sum will approximately equal to 1/4 f of 0 plus f of 0.25 plus f of 0.5 plus f of 0.75. And that gives 1/4 times 9 plus 8.75 plus 8 plus 6.75, which is 8.125. The right Riemann sum will be the base 1/4 times the quantity f of 0.25 plus f of 0.5 plus f of 0.75 plus f of 1. And we get 1/4 times 8.75 plus 8 plus 6.75 plus 5, and we get 7.125. Again, we show the results graphically with the left Riemann sum in red and the right Riemann sum in blue. Even though it appears that the amount that the left Riemann sum over-approximates the area is the same as the amount that the right Riemann sum under-approximates the area, this is not true. It turns out that the left Riemann sum value of 8.125 is a little bit closer to the true area under the curve. We will learn how to find this true area later. Rarely will you have to compute Riemann sums with a great many rectangles because of the time involved, even though it will give you greater accuracy. But you can use your calculator to create a spreadsheet that will quickly generate a Riemann sum with as many as 100 rectangles. The procedure, while not difficult, is better read than spoken, and it's spelled out with a concrete example on page 177 of your manual. The second part of this video will show two other approximation techniques, which will give far greater accuracy than the left Riemann sum and right Riemann sum.